Jai Hind everyone. I am Shruti Jain, Assistant Professor. I am MC Department, Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I am going to discuss today is serializability in Dbms. The subject code is BMC 204. So let's understand first of all what a schedule is. So whenever we are talking about a schedule, we are basically talking about several transactions which are executing concurrently. So when several transactions are executing concurrently, then the order of execution of the operations from various transactions, that is known as a schedule. Like suppose we have maybe 2 or 3 transactions that are running together. Every transaction would be performing a read operation, some of the updates into a particular variable and the write operations. So all those operations in a transaction form a schedule. So those operations are basically the instructions. So a sequence of instructions that specify the sequential order in which the instructions of concurrent transactions are executed, that is also known as a schedule. If we are talking about schedule S of n transactions T1 to Tn, it is an ordering of the operations of the transactions which are subject to the constraint that for each transaction Ti that participated in S, the operation of Ti in S, any operation that is there in any of the transaction, must appear in the same order in which they occur in Ti. For example, if suppose I have 2 transactions T1 and I have the other transaction T2, in this if I am putting a read, I am reading a data item X and then I am writing something with the data item X. Similarly, if I am performing the read operation over here like this, in that case, whatever operations are performed like this over here, those operations are always in the sequential order. So a transaction that successfully completes its execution will have a commit instruction as a last statement. A transaction that fails to successfully complete its execution will have to abort those instructions as a last statement. So a schedule is said to be a serial schedule if all the operations of each transactions are executed consecutively. Otherwise, it is said to be a non-serial schedule. We'll look into it, what is a serial and a non-serial schedule. The types of schedule include the serial schedule and the non-serial schedule. So serializable schedules are the schedules which are either conflict serializable schedule or the view serializable schedule. When we are talking about a serial and a non-serial schedule, that basically means that a schedule is a serial schedule. For every transaction participating in the schedule, all the operations of T are executed consecutively in the schedule. Otherwise, the schedule is a non-serial schedule. So whenever we are talking about a serializable schedule, any schedule which is a serial schedule is a serializable schedule if it is equivalent to some serial schedule of some instructions and transactions. So let's take the first schedule. We have the schedule S1 which talks about 2 of the transactions T1 and T2. So T1, the transaction T1 is transferring $50 from A to B, account A to B, and T2 transfers 10% of the balance from A to B. So if we look over here, T1 and T2 are a serial schedule because all the operations of T1 are executed first and then the operations of T2 are executed. So when we are talking about T1 because has to transfer the amount from account A to account B, it will first read the value or the value in the account A. So reading the value in account A leads to read A and it is to transfer $50. So what it will do, the operation or the instruction over here would be A is equal to A minus 50. So once that 50 is deducted, it will put a write operation. That means it will update the account A. Once the account A is updated, now the next thing is to update the account B by adding $50 to it. So it will first read the original value in account B. Reading the original value in account B would lead to the addition of $50 into it and then it will update the account B. Followed by the transaction T2 which has to transfer 10% of the balance from A to B. So when T2 will transfer 10% of the balance from A to B. In that case, it would read A. It will read the amount from account A. Find out the 10% of that amount in the temp variable, and it will deduct that amount so that we can get the 10% of the amount that is there in account A to be transferred to some other account. So it will update. Now it will read B and will add 10% of the amount to B itself, and it will happen like this. So in this case, the amount in account A is deducted by 10% and the amount in account B is added up with 10% of the amount. This is a serial schedule because all the instructions from transaction T1 are executed and then all the instructions from transaction T2 are executed. Now let's look into another schedule 2 where T2 is being followed by T1. The schedule remains the same. Here we had all the operations from T1 to be executed first and then all the operations from T2 were executed. In this case, it is just the opposite where the instructions are there from the T2 and then the instructions from T1 are executed. So this is also a serial schedule where T2 is followed by T1. The reason over here is both are equivalent schedules. Reason being, these both are independent transactions. Here, the amount in account A is independent of for transaction T2 than in transaction T1. Whatever values are being updated over here and whatever values are being updated over here are independent of each other. Now let's look at the schedule 3. Now schedule 3 has the same thing which we were doing in schedule 1 and schedule 2, but here it is not a serial schedule. Reason being, some of the part of transaction 1 is getting executed, then some of the part of transaction T2 is getting executed and the sequence follows. So in T1, we see that T1 is first reading the data item A and is deducting $50 from A and updating the account A. Meanwhile, transaction T2 gets executed, which is again reading the value of A, which is being written by T1, then deducting 10% of the amount by calculating 10% first and then deducting the amount and then writing the amount into account A by deducting it. So this write A will finally update the value of account A by first reducing $50 and then reducing the 10% amount of the account A. Now again T1 gets executed, which will read the amount of B, update the account by adding $50 to it and then will write the amount that has been updated. With the updated amount, T2 gets executed wherein the 10% of the amount is calculated and that gets added into the temp. We have missed one statement over here. So that statement would be temp is equal to B into 0.1. The statement that so the statement here would be the same one where the temp is added. So the temp value will be added into account B here. So here if we look in all the three schedules, the sum A plus B is being preserved. Whatever value we are getting for A plus B in schedule 1 is same as that of schedule 2 and is same as that of a schedule 3. Now let's look into the schedule 4. The schedule 4 talks about some changes which does not preserve the value of A plus B and hence is inconsistent. Here T1 is doing what? It is reading the value of A and is updating and is just doing the operation and not updating the value of A. Meanwhile, transaction T2 would read the value of A. So in that case, what happens? Suppose the initial value of A is 100. A is equal to A minus 50. This becomes 50, but it is not updated in the database. So the current value in database would be still 100. So this read A would read the 100 value over here and would do all the calculations related to this. Now, read B. Here again, if B initially has the value 100 to it, it will have 100. This write A would only write this value, and this value of 50 gets lost. This write A will not write this value 50, instead it will write the value that has been obtained from here. Read B again would read 100 because initially B is 100. It will add 150 to it, it becomes 150, but this would only calculate B on the basis of this value and not on the basis of the updated value. So in this case, the value A plus B will not be preserved. So when we are talking about serializability, we assume that every transaction preserves the database consistency. That means the sum A plus B is preserved when like in the previous schedules, we have seen that this schedule was not preserving the value of A plus B, but rest of the schedules were preserving the sum A plus B. So a serial schedule of a set of instructions preserves the database consistency. It identifies the data transactions as occurring serially independent of one another, even though they may have occurred concurrently. So we have different types of schedules, schedule equivalence. The first one that we have is conflict serializability, and the other one that we have is view serializability. So whenever we are performing these conflict serializability and view serializability operations, we ignore the operations which are other than the read and write instructions. That means we are only focusing on the read and write operations and ignoring the rest of the operations that are being performed onto the transaction. Now, if we look into the read and write, we get possible 4 combinations with read and write when we are working on any of the transaction. So it could be either the read transaction operation, it could be the read and write operation, it could be write and read operation, or it could be the write and write operation. So whenever any of the transactions, suppose we have 2 instructions ij and ii and ij of 2 of the transactions ti and tj respectively. So in that case, both the transactions, this is with ti, this is with tj, both the instructions of ti and tj can read any data item and it will not conflict. Conflict arises when there is a write instruction included when in the schedule. So when both the transactions have the read instructions, in that case they will not conflict. So here ii and ij will not conflict. But if any transaction is performing a read and the other transaction is performing a write, in that case they conflict. It could be either read first and then write, or it could be write first or read later. Even if there is any of the 2 write conditions, then also it will conflict. So if a schedule S can be transformed into a schedule S dash by a series of swap of non-conflicting instructions, then in that case we'll say that S and S dash are conflict equivalent. So we have 3 rules which show that if 2 operations in a schedule satisfy all these 3 conditions, then they are said to conflict. Number 1, they belong to different transactions, as we have seen over here. This is with ti, this is with tj. They are accessed at the same time, and at least one of the operation is a write item. When we are talking about view serializability holds 3 conditions. The first condition says, if ti reads the initial value of q in schedule S, then the transaction ti must also read the initial value of q in schedule S dash. That means, if suppose we have S and S dash as 2 schedules and we say that these 2 schedules are view serializable, in that case, if the transaction here ti is performing the read operation, then that transaction ti should perform the read operation in S dash also. The second one says, for each data item q, if the transaction ti executes read in S and that value was produced by a write in tj, then the read operation of ti in S dash also must read the value of q that was produced by some write operation. That means, if suppose we have the write operation executed first on any data item and then the read operation is being performed in S, the same thing should be executed over here with write at first and read later on. The third says that for each data item Q, the transaction that performs a final write in S should also perform the final write in S dash also. So here, if the final write is being performed by T2 transaction, like write Y, in S dash also it should be performed by the T2 transaction as write Y. So if these three conditions are satisfied, then we say that the two schedules are the view serializable schedules. So if we look at the example over here, we have a schedule where we have T1, T2 and T3 as transactions. This A is, suppose a value of A is initially 100, is being read as 100. Then write A is performing some operation, that is, suppose 40 is being deducted from this, we get the value of 60 over here. Again, a write operation is being performed, which is again deducting 20 from account A. So we finally get the value of A as 40. So write A would produce 40. So in this case, this would be a conflict serializable schedule. When we check for view serializability, we'll see that initial read is same as that of initial read over here. Final write is same as that of final write over here. Here, both the writes, if they are even swapped off, then also the final A write value would be 40, and hence this is a view serializable schedule. When we are, so if we look at these two schedules, schedule 1 and schedule 2, these both are conflict serializable schedules, because this schedule is not a serial schedule, but it can be transformed to a serial schedule in this manner. Testing for serializability. Whenever we are checking for conflict serializability, we check for three of the main conditions. We try to make a precedence graph where the edge is from T1 to T2 when any of the transaction is performing read after write or write after read or write after write. So read will not have any effect, and all other transactions or all other instructions would be an effect into the edge, would be converted into the edge from Ti to Tj. Suppose we have this as an example. We have this schedule where we have T1 to T5 as transactions. We'll look into it, how the precedence graph is being formed. In case we have a cycle in the precedence graph, we say that it is a conflict serializable schedule. If there is no cycle into this graph, then we say that it is a non-conflict serializable schedule. So let's look into this. We'll start with read X first of all. Now we'll check this X is being used by T1 in any of the cases. No. This X is being used by T3. No. X in T4, T5. No. So this is safe and can execute without any conflict. The next operation that we have is read Y. We'll check for Y. We have in T2 read Y, because read does not conflict, it will not conflict. But we have write Y also over here in T2. In that case, we'll have an edge from T1 to T2 like this. We'll check for T3. There is no operation on Y. Here we have an operation on Y, read Y, no conflict. But write Y will conflict over here. Write Y will conflict. So we'll have an edge from T1 to T3. So this edge would be from T1 to T3. For T5, there is no operation on Y. Moving to the next one, read Z. We'll check for Z. We have write Z over here, which will be a conflicting one. But we already have an edge from T1 to T2, so we'll not draw any other edge. For this, we have T1 to T3 an edge, because there is a conflict from read to write. So we have an edge from, sorry, that was T1 to T4. So this is T1 to T4 for this one. T1 to T3, we have write Z. So we'll have T1 to T3 an edge. Read Z, will not conflict with read Z over here, but read Z will conflict with write Z over here. We already have an edge from T1 to T4 and hence no other edge will be formed. For T5, there is no operation on Z, so nothing would be done. Coming to read V as a next step, no operation on T1, no operation on T2, no 3, no on T4, so it is safe. Checking for W, no operation on T1, no operation on T2, not on T3 and T4. Similarly for this, there is no operation with T5. Moving on to read Y, we have read Y conflicting with write Y over here. So we'll have one edge moving from T2 to T1. This read Y does not conflict with T3, but this read Y conflict with write Y over here. Read will not conflict, but read write will conflict. So this read Y will conflict from write Y. So we'll have one edge moving from T2 to T4. No operation on T4. Next we'll check with write Y. Again a conflict with write Y to write Y, but we already have an edge from T2 to T1, so we'll skip. No conflict with T3, but write will have a conflict over here, but we already have an edge, so we'll not make any other edge. Now we'll check with write Z. Write Z will not conflict with T1 because no other operation on Z. But T3 and T2 will conflict, so we'll have an edge from T3 to T2. This write Z will not conflict with read Z, but this write Z will conflict with write Z. So we'll have an edge from T3 to T4. No conflict with T5. We'll check with read U. Will not conflict with T2, T3, T4, T5. Next, we'll check with read Y. Read Y will conflict with write Y. So there is an edge moving from T4 to T1. So we'll have an edge moving from T4 to T1. No conflict in T2, T3 and T5. Checking with write Y, again a conflict occurs with T4 to T1. We already have an edge. No conflict over here, no over here, no over here. Moving to next, read Z. No conflict with T1, but there is a conflict from T4 to T2. So we will draw an edge from T4 to T2. No conflict in T3 and T5. Similarly, we have write Y. Write Y will not conflict over here, will not conflict over here, will not conflict, will not conflict. Then read U and write U will not conflict anywhere. Similarly, write Z will not conflict over here. So in this case, if we look over here, we have a cycle being formed in this manner. This is a cycle being formed, and hence this is a conflict serializable schedule. So a schedule is a conflict serializable if and only if its precedence graph is acyclic in nature. So because we have a cycle in the previous schedule, in that case it is known as a non-conflict serializable schedule. If it does not have a cycle, then it is known as a conflict serializable schedule. So in this case, if we look over here there is no cycle, so we got two schedules in this manner. So that's all for today. Thank you.